Okay. So homework 6 was finishing the longitudinal multi-level model, right? Anyone have any questions left on that you want to talk about? Ariel, I have a note here about interpreting variance components specifically for 5A.
Yeah, thank you, Sarah. I think I can't remember if that was 5A or 3A. Let me pull up that question that I have. Sorry.
I'm going to open mine up. I'm going to make mine bigger too. Oh, that's big. And it's small again. This is kind of confusing. Homework 6. Okay. It's bigger. Bigger.
Okay.
Come on, computer, you can do it. Okay.
So I think, Sarah, it was just for prompt 3. It says, is there significant individual level variation in the linear trends of illness severity across time?
Okay.
And I'm not sure. So
yeah, so across time is this OBS.
Mm-hmm.
So it has a fixed effect. So that's the marginal, like overall, yes, there is change over time. But it's when it says specifically, is there significant individual level variance?
Mm-hmm.
That would be right here.
Okay. I copied both of those, but then I was like, I want to make sure I know how to interpret them because I know the ob slope is significant, but then I don't know if you just say
the ob's fixed slope is significant, but the random effect or random slope of obs is not significant. So this is telling us, yes, there is change over time, but because the variance component is not significant, that tells us that it does not, it's the same, pretty much the same for everyone. It's not like some are steep and some are flat.
Oh, okay. All right. Thank you.
So, and it's an individual level effect. And so right here it says the variance in ID op. So that's how much variation there is among individuals in the slope or the effect of over time.
Okay.
Yeah.
So that's really helpful. Thank you, Sarah.
Yeah. Any other questions while I have it up and we're here? If you guys put your questions in the discussion board, that helps me make sure that we get them addressed. Either I'll type them there or we can bring them up in class. That helps it not like fall through the cracks. Because that's a really great question. I mean, all your questions are great, everyone. But. Okay. Just peek here at the schedule. So you guys, I want to take a second and appreciate how far we've come now that we're past the midpoint of this class. So everyone came into this class with a very different background and experience level with all of these things. So let's just review. We started with what is our studio? How do we get them installed? How do we get our data in? We reviewed ordinary least squared regression. We extended it to 2 levels, both cross-sectionally and longitudinally. And I mean, that's not a little bit. That's a lot of information you guys have consumed. And to have a 100% down pat, be an expert right now is like, don't worry that you're not there. I've taught this class 6 times, and every time I teach it, so much more makes sense. And if I'm away from this stuff for a long time, it starts to fade out like anything. So don't be concerned if you don't feel like an expert yet. I think you guys are understanding a lot more than you think you are. I mean, I think if you really focus on where you were 5-6 weeks ago, you guys have made a drastic change in your understanding, a huge growth. So right now we're here at reviewing the generalized regressions. So we covered a lot of logistics last time, and a logistic is key because the multinomial and ordinal logistic build right off of it, and a lot of those key understanding apply directly to Poisson and negative binomial as well. And the reason we're having this pit stop on these generalization, quite the pit stop, is because next we're going to go into GEE and generalized estimating equation and generalized multi-level models. And both of those use all these generalizations, specifically like logistic. Now, covering all these types of regression can be 2-3 credit classes. Like in the math stat program, you take regression, like linear regression is a 3 credit class, and then the generalizations are a 3 credit class in themselves. And we're only having a week-ish to cover them. So you're probably not going to get to be an expert if you haven't covered these before or in very, very little depth. But if you can get through logistic regression, and that's why the homework assignment only covers logistic regression, you will be okay and you'll be able to move forward. So there is no homework assignment that asks you to do Poisson, multinomial, negative binomial, any of those. But in the encyclopedia, I'm trying to put up all of Hoffman's examples in R so that you could reference them in the future. So we're going to kind of cover them briefly, superficially a little bit, those other methods, enough so that we can understand them when we go into the multi-level. And we will focus mostly on logistic. Part of that's because it's the foundation of the other ones, and part of it's because that is the bulk that I see published and used in real life. And again, even if you understand logistic, you can extend to the other ones because that's the strongest foundation. It has all the key parts. So just to heads up, I talked about this a little bit, but after next week, I will be gone for a week. So November 3rd and 5th, I will not be here. I'm going to ask that you guys still attend the time during the Zoom call, but without me to work on homework assignments. And I will be able to answer some discussion posts in the evening, but I just won't be able to be on Zoom during that time that we have class. It might not take you the whole time, but I don't want it to be a dead point in your semester. But it will be wrapping up GEEs in the Gaussian or continuous distribution and moving into them in the generalized form. So I will record, my goal is to record like 45-minute lectures for both of those days next week so that when I'm gone, you could jump on and it would be either you can, I'll let you know and then I'll ask for you to vote. Either you can jump on and watch the video together and have one person sharing their screen, stopping and starting it to discuss, or you can watch the video on your own time and then just get on to do the homework. Maybe think about that and I'll send the options and ask for you guys to vote unanimously or blindly, so I don't know who's who on which option you would rather do. I just want you to have a meaningful experience while I'm not here, but I don't want to waste anyone's time, of course. You guys have stuff to do. But I don't want to cheat you out of that learning experience because GEEs are very common. In fact, Joey, do you want to say what you just said right before class?
Sure. I was just reading a research article and they had done a GEE model and I was reading through the analysis and things. I was saying to myself, this sounds really similar to what we've been doing with mixed models, but I didn't really know how it was the same or how it was different. So I asked Dr. Schwartz and she's like, yeah, we're going to do that one. So
next week. So they just kind of a teaser, GEEs take less computational power and they're easier for an old computer to run. And so they caught on years ago because people's poor computers back in the day could do them. It used to be to do a multi-level mixed effects generalized model, like we're going to do these GLMMs, you had to have a supercomputer back in the day. Right now, every one of your computers is going to have a fine time, but historically, the GEEs caught on earlier and people started learning about them and actually using them earlier because that weren't so demanding to have a fancy computer. And they're informative. They're really useful. So we'll do that, especially when you have sparsity. So they're good things. Shrink this. Let's go to Canvas. Come on, Canvas, where are you? Oh, it's on the other screen. Okay. So in the discussions, I got to do some major grading to catch up. You guys are moving faster than me. So today is supposed to be due. It was supposed to be due at 4 o'clock today, but do them if you haven't already. The 2 discussion posts, one on homework 6 and one on the logistic regression from Huffman's chapter 2 and 3. So those are supposed to be due now, as well as homework 6 is supposed to be due tonight at 8. So I think most of you turned it in. So homework 7 and this new is due on October 29th. That's a week from today. So you have a week to work on that. And remember, you have the 2 options. You either can do the logistic assignment that I wrote, or you can create your own assignment, or heck, I'd be happy if you just applied any of these to data you care about. Make your own assignment with data you care about. So that's not just a busy work. So that's homework 7. It's single level. So this is, I just made this go live. This is the new discussion post for the new set of readings. So this is Hoffman's chapters 4, 5, and 6. So we just read 2 and 3. These are the next 3 chapters. Now you can read this with some skimming involved, if you like. Like I said, we're not going to focus heavy on this, but we will talk about it. So there are the 4 PDFs for chapters 4, 5, 6. And then I have my 2 examples in the encyclopedia of doing these kinds other extensions of logistic regression. And I have bookmarked for you guys 2 videos to watch. Now they're both about an hour long, but you only really need to watch half of each one. So this first one is on ordinal and multinomial logistic. The first half of it reviews logistic regression. I think it's well done, but if you think you have logistic regression done, you can skip through the first half hour and just watch the second half hour. So I put some minute markers here on where they cover. So again, I put this one on. You can watch it to review linear and logistic regression, but I highly suggest you watch about the last 23 minutes, 30 minutes that cover multinomial and proportional odds. So that's this first video, and this is Karen Grace Martin, and both of these they're labeled The Craft of Statistical Analysis is the YouTube page, but they're both from the Analysis Factor website. I think I've had you read some things or posted some things from their websites. It's really good. The second video is from Jeff Meyer, same series, same website, and he covers Poisson and negative binomial regression for count data. And he walks through an example of doing both of them to determine which one's a better fit to his data. But this one's an hour long, but the good news is you only need to watch about the first half hour, because after the 39-minute mark, he gives a list of sources, he plugs his other videos, and he does a Q&A that people are like sending on a Zoom chat into him. So you don't have to watch the rest of that. So the last half hour you can skip. And then some supplementals. I have Tyson's GLM video, which aligns somewhat. And then here are some other series from epidemiology. And let's see, who was it? Ariel? No. Who? Somebody linked. Alex, was it you that linked? Someone linked one of these videos in the discussion. Anyway, this first one on Poisson regression. Somebody, I didn't write down.
Oh, yeah, I'm sorry. It was me, Sarah.
It was you, Ariel.
Already had one. I think Chung Su asked a question about it.
Yeah, about the Poisson and count. Mm-hmm. So this website series YouTube channel only goes over Poisson, and these are 20 minutes, 31 minutes. I thought they were great, but depending on your time constraints, do what you can do. But if you see Poisson regression being something that you will probably come across or want to think about using, there's definitely some more material for deepening your understanding about that type of regression. Okay, good. So you're wrapping up and moving into logistic. You've done the logistic reading and video watching for the most part. You're ready to start the homework assignment. Let's look at some extensions of logistic regression, shall we? So I am going to go to, gotta set the timer. Gotta set the timer. Let's see. Half hour? Right? Okay, half hour. Start. Okay. So I'm gonna come over here. Oh, if I go to this link here for the encyclopedia, it shoots me straight to volume 5. I want to go to volume 4 for the single level regression. So I'm going to click on Encyclopedia's home website and the volume links and get to volume 4. Okay. So here's some logistic regression. Didn't update last night. Okay, we're gonna go, the Hoffman one is not on here yet. I'll get it up there tonight, but we'll look at these that are not out of Hoffman. That'll be good. Then the Hoffman ones will be new when you look at them. Why are we not? Make it bigger, make it bigger. Okay. Okay. So here's the background to this study. I think doing it at example based might be more helpful than just rehashing theory. So this is a data set that has 263 rows and only 4 columns. So it has very few variables. This is from 1977 survey of in Canada. This is the year I was born, because I'm old. So the dependent variable here is the labor force participation. So this is where it's different than anything we've done before. The outcome dependent variable is not continuous, and it has more than 2 levels. It has 3 levels. So either the people, and I think is this women only? Yeah, this is women in Canada. They were either not working at all, working part-time, or working full-time. There are 3 categories. Now, if there were only 2 categories, we could do logistic, working, not working, but they're splitting it out into 3. Now, is there inherent order to those categories? Mike, you're shaking your head yes. How so?
Well, I see that those 3 is actually a spectrum of full-time to no time. So it seems to me like part-time is somewhere in the middle.
Yep, that's reasonable. Now, there was some discussion on the board, and I was really glad to see it, about how do you know if you should treat your dependent, like a lot of times people will have a count, but they treat it as a continuous scale. And likewise, sometimes we have a percentage and they treat it continuous, but it's skewed so that we have the ceiling effect. That's not truly normally distributed. And what happens now, if you have a percentage and everyone's kind of in the middle and it tapers off, and if you plot the distribution of their like percentage correct on a test, if you get a nice kind of bell-shaped curve, you're probably okay to do normal Gaussian regression. But if you plot your outcome and you get a very skewed, like max is 100%, you've got that bound or their upper limit, then treating it as continuous is probably not going to be great. And if you do your residual diagnostics, they will look horrid. The same thing happens if you have your outcome is a count, and most people are between 0, 1, 2, 3-ish, and you treat it as if it's continuous, even though they're like bounded by the lowest it can go is 0, and you have people that are 0 and 1, like a lot of them, and very few people it's skewed, and whole numbers only, you can treat it as continuous. But if you look at your residual diagnostics, they might be horrid. So people, there's no stat police that are going to jump down from the ceiling and say, hold it, that count should not be treated continuous. Or sometimes if you have a count, but most people are in the 30s and 40s and you plot it and you get a nice bell curve, it's fine to do it. So it is on the researcher running the analysis to check the residual diagnostics and to make that judgment call whether your outcome, even if it's a count or a percentage, is it acting enough like you can be treated as if it's continuous, or is it acting not continuous-ish and needs to be treated in a different manner? When in doubt, fit it both ways. Look at the 2 residual diagnostics, compare the deviance or the residual, the RMSEA. We've got fit statistics, we can compare models. Usually people will treat a variable outcome, an outcome variable, as if it's continuous, even though they know it's not unbounded between negative and positive infinity and not decimal numbers. They'll treat it continuous because they don't know any other option. And that's not acceptable. You should know the other options that are out there, or collaborate and reach out to somebody else, like the Stat Studio. That's why I have a job, right? There are plenty of people that can help you, but don't be an ostrich. Don't bury your head in the sand and just do the only thing you know how. Okay. So a lot of this class is growth in knowing that there are options out there. You can, in it, generalizations, multi-level, if your data doesn't fit the mold for the tool you have, go look for another tool. And hopefully this class will give you exposure to tools, but you're not going to be an expert in everything. Heck, I have a PhD in statistics and 15 years under my belt, and I'm not an expert in everything. Statistics, not even close. I see new stuff every month, every week. That's okay. We're learning and growing and enhancing our toolkit. So in this example, we could have measured the number of hours that each woman worked, and that would have been bounded between 0 and maybe 40-ish as a top number for hours worked. And that would probably be, would it be continuous, do you think, if we looked at hours worked? What do you think it might look like? Anyone have any kind of gut feelings for women in the 70s in Canada? If we did hours worked, where would we see the distribution like? What?
Skewed towards the low end.
You'd probably have a lot of zeros because in the 70s, a lot of women were housewives. And then you'd have probably another heap or tape in the middle, part-time, and a few humped at the 40 hours working full-time. You'd probably see some not bell curve. And so even though you could have gathered continuous data, if the hours worked fall in more or less 3 rough categories, then treat it as such. In the 70s, women were either not working a little bit, or they were having to work full-time at a traditional job, more or less. There's a lot of spectrum in there. There's definitely an ordinality, but those are our 3 outcomes. So we want to know, what is the relationship between these predictor variables? What predicts or what affects what is related to the amount a woman works? And these are the only variables we have, 3 other variables we have in the data set to use. We have how much money the husband makes, and it's in units of $1,000. So this is annual income. And remember, it's the 70s when you see the numbers. It's not the 2020. And then there's a binary predictor about whether or not there are children in the home. Do they have kids at home? What do you think? If there's kids at home, how is that going to affect how much the mom works? The woman works? How much the husband makes? And the last one here is the region. Now this is in Canada, so we have Atlantic, British Columbia, Ontario, Prairie Provinces, and Quebec. So that's a 5 category region variable. Now, does it matter what kind of variables our IVs, our predictors are? No. We have one that's continuous, the husband's income, one that has 2 level, yes or no, they have children, and one that has 5 nominal categories. We can have any of those for predictors. The importance for choosing the model is what the dependent variable is. And here we have 3 factors. Now, on the discussion board, I think it's this one. Right before class, I was answering some things. And down in here. Is it in this one? Yeah, right here. So I made a little box, little table. Where is it? Aha, right here. So both multinomial and ordered logistic, both of those are good for doing a 3 or more level factor outcome. the decision between the two begins with, is there order to the categories or not? Now there's an extra addition here I probably add it in. Let's see. Is that for ordinal logistic regression, you have at least 3 categories that do have order, and the odds are proportional. And we'll read and talk about that some more. So there's our setup. So here is our data set. So participate, that's how much they work. So this first woman is not working. Her husband makes $9,000 a year. Children are present in the home and they live in the prairie area of Canada. Okay. Again, this income is in how many thousands of dollars the husband makes back in 77. Okay. So I declared some factors, added some labels, did some descriptive work. Here we go. So here I've taken the dependent variable, how much the woman is working, not at all, part-time and full-time, how much wife works. And for each of those 3 groups, I plotted the distribution of the husband's income. And there's a lot of overlap here. Visually, looking at this, does there look like that there's a relationship between how much the husband makes and what level of work the woman is participating in? Let's look first at the blue for full-time. When the wife is working full-time, what is the husband's income like? Which of those 3 curves is it? The blue one. They're kind of wiggly, but it's the one that's like close on the lower end. So the wife is more likely to work if the husband's making a little bit less money. Maybe, it's hard to know, but that's one of those things we can test. Okay, here's another plot. I've got the 3 groups. And here's husband's income. So it's the same information I was plotting before. The red lines are the averages. Are the average income in those 3 groups different? A little bit. Full-time does look like the husband's making a little bit less. But the red line is the average. But by putting all the dots, we can also see the spread. Where is there most variation?
In the not at all group.
When they're working not at all, more spread here? Yeah. Okay, here it is as a box plot. So part of this is showing you different plots you can make. Here's a violin plot. If you ever need to make these, here's some example code for you. So here's children in the home. So anyone see a relationship with children in the home and what the wife's doing? How would you talk about that descriptively?
It looks like there's a higher number of women who aren't working at all for when there are children.
Yeah, when there are children in the home, a greater chunk of the women are not working. And when there are no children, there is a bigger chunk who are working full-time. Now, look at the total size of those bars. They're not the same. So what is that telling us? That the present bars stack up higher than the absent bars.
In general, more people have kids.
Yeah,
Or
more
more
the households
women.
have children than don't.
Yeah, more households in general have kids.
So can I compare like this blue bar to this other blue bar? I can compare them as far as the total number, but what might it be nice to do?
Convert it to like a percentage
Percentages.
or something.
Yeah, we can stretch it out so we make it percentage or proportion. Now we can compare straight across the makeup or the breakdown. So there's code here. I mean, this one's very short. This one I added a whole bunch more. If you want to learn how or ever are interested in making any of these kinds of plots, because they can help you understand your variables one at a time and two at a time before you get into any fancy model. Okay, so, and here's for regions. I do a lot of those. Okay, so this has been not a problem, but a scenario where you have an outcome with more than two levels. People have wondered for a long time back, how was the best way to model that? And the first attempt at modeling three-level outcomes was today to say, well, let's do it with a couple different logistic regressions. So if there are three levels, we could do A versus B and C. So compare full-time to not full-time, and then compare part-time to collapsing the other two, and then compare not at all to the other two. Sometimes those are called hierarchical or nested logistic regressions, and it's what people started doing first. And it can work, but there's a drawback to modeling it that way, is that we're modeling how many different logistic regression models? 3. What do we know about when you fit more than one model? Fitting 3 models. Now we need to worry about, bring up any red flags, making multiple models.
Alpha inflation.
Inflation of type 1 error rate. Multiple comparisons lead to inflation of type 1 error rate. So it's not a parsimonious way to do it. It's actually not a very good way to do it, but it is a way to do it. So I've gone through and I made 2 different versions of the working variable. I said, are they working at all? Yes or no? And if they are working, is it part-time or full-time? So I made, instead of 1 3-level variable, I made 2 2-level variables by collapsing the categories 2 different ways. So I can do those models. So here, are they working at all? And then put in the 3 predictors. And again, like this is just logistic regression. So I use the GLM and tell it the family binomial with the link logit. And then I can do it. Oh, here's a cool command that you guys might want to know about in R. It's kind of handy. So I fit my model and I called it fit GLM1 because it was the first model I ran. If I say drop 1, test equals LRT, it takes that model and it drops the first variable out and does the likelihood ratio test. And then it puts it back in and it takes out the second variable and it does a likelihood ratio test. And then it goes back to the original one and it takes the third variable out and does the likelihood ratio test. So this is another way to, so this is essentially, since I had 3 predictor variables, it's like it's fitting the model, here's the original time, and it's fitting it 3 more times, each time leaving out one of those variables and then doing all 3 likelihood ratio tests at once by dropping each variable out 1 at a time. Okay, so let's see. The first variable, is it significant? The p-value is the last number. Yes. Second variable, is it significant? Yes. Third variable, is it significant? No, it's not. Now it just said, it's just the first, second, and third variable, but let's look what they are. So husband income, is it significant? Yes. Children, yes. Region, not so much. Okay. And so, yeah. So then I can fit another model. Now, what have I done with this second model? I'm still doing, are they working at all? What have I done with, what does this do in R when I do this capital I? What does the capital I do?
You internally centered it?
Internally centering the variable at 14. And I did 14 because on that's the average husband income is about $14,000 and it's already in $1,000. And then children's binary, so I just left it that way. Okay, now I get some Wald test. According to the Wald test, are both of those predictors significant? Yes. Okay, now, ooh, it's here. I put this here. That's why it was working. Okay, I need to delete that. So I can make a table. Now we saw this extract GLM EXP function, the TechReg helper function last time. When I first wrote it, I just wrote it here on the web page, and then I put it in the package. But so here we go. So I extracted the parameters and exponentiated them. Why do we exponentiate the parameters estimates in logistic regression? What good does that do?
Interpretability.
Interpretability, because it goes from, the parameters start out on what scale?
Log likelihood. Or
Log
Logit.
odds ratio, which is terrible to think about. So when we exponentiate it, it goes from log odd ratio to plain log odds ratio. So let's interpret this. So this is the intercept. And the intercept for the categorical variable, it puts it at the reference category, so no children. And I centered husband's income, so the intercept goes with when the predictors are 0. Intercept is when predictors are 0. For categories, variables, it means it's the reference category. For continuous variable, it's whatever 0 is. So for households with no children and the husband making the average 14 grand, the odds the woman is in the workplace at all is 2.1. So it's about 2 to 1. So 2 to 1. So 2/3 of the women are working when there's no children and husband's making the average 40 grand. That's how you the intercept tells you the odds. The other exponentiated betas tell you the odds ratios. So let's look at husband's income. For logistic regression, what do we compare the exponentiated beta to? Usually we compare our betas to the number 0 and say if it's positive, it makes it go up, and if it's negative, it makes it go down. But in logistic regression, we compare the exponentiated betas to the number 1. And if it's bigger than 1, it's going up. And if it's less than 1, it's going down. So the key here is we got to compare it to 1. That's why when I put a custom note here, I said we're looking for at the value of 1. So here for husband's income, it's smaller than 1. The exponentiated beta is 0.96. So how much lower is it? 0.04. So for every $1,000 more husband makes, the odds the woman is working goes down 4%. Again, for every $1,000 more the husband makes, the chance the woman is working at all goes down 4%. Why 4%? Because 0.96, you compare it to the number 1, and it's lower by 0.04. Okay, children in the home. So this is comparing children in the home versus not in the home. Ooh, look at that exponentiated beta. Compared to the number 1, it is
79% lower.
Almost 80% lower. So if children are in the home, the odds the woman works goes down 80%. Okay. So it's written up here. Okay. Here I've done the interaction plot. So I've done an interaction plot. The x-axis is husband's income. Remember, the pred has to be a continuous variable, and the moderator can be a categorical variable. So here we go. Let's look at the blue line first. There's no kids in the home. Now, when you use this interactions, it'll automatically convert from logit to odds ratio back to probability. So notice the x-axis is in terms of probability from 0 almost up to 100% to 1. So this blue line, what's the chance the woman is working, period? What happens to the probability the woman's working? What's the relationship with husband's income? The more the husband's working, the probability the more the husband is earning, the lower the chance the wife is working. Now let's look at children. After controlling for husband's income, when there are children present, there is a 80% lower odds or a lower probability that she's working as well. Now, when we did the raw plots, we saw the variables one at a time, but this is combining both variables together. Now, I added a bunch of stuff in here, and that puts it at a more publishable quality plot. I've also added a vertical line here. What number do you think that's at?
That's
14.
your 14,000 again.
14,000, because that's the average husband income. So these are the intercepts right here, because I centered at 14. So that's why I drew that line on there. Okay. You can get the effects, probabilities. Here's another one. Okay, so this is one logistic regression, just looking at yes or no, she's working at all. And then I went and did it, is she working full-time? And I did it again. And it's a lot the same thing. I don't want to, here's the plot of that. Now let's look at it here. Here, it's the predicted probability of women being in the workplace full-time if they are working. So for women that are working, what's the relationship with husband's income and children in the home? The more husband makes, the less likely woman's working full-time. And when there are children present,
Less likely.
yeah, so look down here at 0. If there are children and the husband's making modest amount, she's not working full-time. This was the 70s. We'll just say that, okay? Says the woman who makes more than her husband. Okay, so that is handling this research question, this data, with 2 separate logistic regressions. We know how to do logistic regression, but doing 2 different models, not the best way to go about it. So this is where we're going to do it as multinomial, and then we're going to do it as proportional odds to show the difference. If we only get through this one example today, I'll be happy, but I'd like to touch the other one if we can. Okay, so multinomial regression fits a single one model where you have multiple outcome groups. Multinomial, the groups don't have to have order. There's no assumption about order or proportionality. We're going to have to choose one as a reference category. In this scenario, I'm choosing not working at all as my reference category. So we have working part-time or full-time, both compared back to not at all. You have to have a reference category. So we're going to get a set of betas for each of the other categories, full sets of betas. So let's see how we write the code. We're going to use this nnet package. I believe it's one we got on the week 1, so you should have it. And the command is multinom. Because this function only does multinomial, you don't have to put family equals or anything like that. It knows that it is doing a multinomial data set. And for this to work, your dependent variable in your formula has to be a factor. And whichever level is the first level, that will be your reference category. And then the rest of the formula is just like we're used to writing. Now I'm centering husband's age at the mean of husband's income at the mean of $14,000. Children is the binary, and region is that 5-level variable. So when I put that and then what the data set is, now I've saved it. So it shouldn't be giving me any output, but when you run this, it actually does give you some output. And this is information about the iterations. So this solves these, I mean, I don't know all the nuts and bolts, but it's iterating, solving this problem, maximizing the likelihood, which there's the whole probability versus likelihood. So it says we have the data, given this data, what's the most likely parameter, assuming the distribution of the parameters is normal. And it has to do a lot of iterations. So it gives you some information about how many iterations it took. I always ignore this. I don't care as long as it ends up saying converged, we're good. So here I add summary. Now in the summary, I told it not to tell me the correlations because I don't want to look at them, but I did say, give me the Wald test. Now check out this outcome, this output. Let's just look at the coefficients part here. How many coefficients did we get? Intercept, husband's income, children's present, and the 4 regions compared to the reference category. But for each of those terms, we get 2 parameters. We're about ready for break. One for the part-time, one for full-time, both compared back to the reference category of not working at all. So you get double the parameters. So why is this better than fitting 2 logistic regressions? It's because it's fitting all of the parameters at the same time instead of fitting them in 2 separate sets. But you can think about it as it's doing 2 logistic regressions for part-time compared to none and for full-time compared to none. And it's just giving you all the results together. In this one, the region's not significant. We already saw that. So I'm going to drop out region and just do the 2 main predictors. It's a little easier to look at now. So how many parameter estimates do I get? Got the intercept and 2 predictors. That should be 3 parameters, but I really get 2 sets of 3. Now you can do the ANOVA command to do a likelihood ratio test comparing nested models. So model 1 had the 2 predictors, children and husband's income with region. The second model dropped out region, and we can see, is region significant? Not significant. It didn't make it fit better. We can use the compare performance and rank them to see which one fits better as well. So everything we've already learned still applies here. Now, the parameters it fits, so here's our model right here. The parameters it fits, these are not on the probability scale. This is multinomial logistic regression, so they're on the logit scale. How do we get rid of that logit scale?
That special package.
Exponentiate.
Exponentiate. And yeah, so there's a lot of jumbo here. So I extract, so if I put in knitter just the name of the model, now I did some labeling here. You get a set of parameters for part-time and a set of parameters for full-time. So you get an intercept and 2 beta. No, these are not betas. Well, this is just here in TechReg, I just put the name of the model. So when you just put the name of the model, it does the betas with the standard errors. But you can use, no, the extract function doesn't work, that's right. So you have to get the exponentiated betas, you have to say the name of the model, pipe coefficient, and then pipe exponentiate. So here is the set of the regular coefficients. And these are on the logit scale, so they can be positive, a huge number, all the way up to negative, a big number. But when you exponentiate, they're always going to be around 0 to 1 or 1 and up. So let's see if we can interpret these. For part-time work, what is the role of children present? What do we compare this exponentiated to? Which value? 0 or 1? 1. So for part-time work, what does having children present do? It makes it go up how much?
2%.
Up 2%. So if there are children present, the odds of working part-time is 2% higher than the odds of not working. Why would they work more why would there be a higher odds of working part-time than none at all if there's kiddos?
You might need the income.
Ah, Jill, kids cost money. I've got 4. They're cute, but they're expensive. What is that role for full-time though? Compare it to 1. If there's kids in the home, what happens to the odds of working full-time? goes way down. Because if you've got kids in the home, it's hard for mom to work full time. I can attest to that. Okay, so you can get the exponentiated coefficients out, but you can't use the TechReg helper function. I'm gonna have to work on that. Okay, plots make everything interpretable. Now, before we had to look at two different plots. Here, now I did this yesterday and then I found an easier way to do it. So don't worry about all that code. I'm going to simplify it up for you a lot. Here is the picture. Let's see if we can look at this picture and figure it out. Okay. So how many different levels of the outcome are there? Wife working. It could be none, some, full-time. Those are the different lines. Now, what's our y-axis? We plotted it back to the probability scale. That's why on the probability scale are these straight lines. On the probability scale, they're the S's, but some of them are stretched out quite a bit and some of them are squished. So this blue one, you can kind of see it's an S backwards. The green one, it's an S this way, but it's stretched out a little bit. That red one is stretched way out. So let's see, we've got husband's income and children. Let's do when children are not there. Let's look at this plot. Ooh, let's see if we can figure this out. So I put on the line of 14 and I also put on a horizontal line of 0.5 because that's 50-50 chance, 50.5 probability. So let's look in this left side of the first panel. So this is when children are absent and husband's making less than the average. What one of these colored lines is the highest? The blue. So when there are no kids and husband's not making much, wife's probably going to be working full time. It's like 80% chance down here. What happens is we move up to the higher end of income. As husband makes more, what happens to full-time work? And instead of working full-time, the wife's going to be working. Green is not at all. Not much part-time work going on here. So when children are absent, if husband's not, wife is working full-time when husband's not making much. Wife is not working once husband makes about, it looks like it crosses over about 20 grand. Okay, let's look when children are present. Whoa, what's the biggest difference between these two panels? Which color?
The blue and its intercept.
Yeah, look at the blue line. What's blue line standing for? Full-time work. When there are children present, what's the chance the wife's working full-time? Really, really low, no matter what dad's making. Let's see, the red one's part-time. Is the wife working part-time? Not much, but a little bit more as the husband makes more. That's kind of a head scratcher. This is back in the 70s. It doesn't look like many of the wives worked part-time. If there are children present, the most likely thing for the wife is that she is the green line, not working at all, no matter what husband's making. That's the highest probability outcome. You guys like interpreting the odds, the logits, the parameter numbers, or do you like interpreting the plot? Ariel's got a smile.
I like the plot better.
Yeah, I'll get the easier code up here for you to be able to use because that other code's convoluted. Okay, so this is plot version 1, and I did another plot. So this plot has paneled by whether or not there's children. I'll just tell you, there is always more than one way to make a plot. It depends on what you want to focus on, the story you want to tell. And this is a very helpful, if you're saying, given that there's no children or given that there are children. But another way to present this plot could look like this. I have a panel for each type of working scenario, and I have a line for children present or not present. Sometimes this tells the story better. So women not working at all. What's more likely? The red line, which means kids are present. Part-time work, whether or not there's kids, it doesn't make a difference. Part-time is pretty low across the board of husband's income. Full-time work, when is it the highest chance that the woman's working full-time?
When there are no kids.
No kids and dad's making a little bit, or husband, there's no kids. I was saying dad. Okay. So sometimes paneling it one way makes it more clear. Sometimes paneling it a different way makes it more clear. Personally, I tend to try it multiple ways to see which one makes it clearest. When you have more than 2 variables, there's lots of options to try.
Will you scroll? Did you just put will you scroll up in your code?
So in this code,
It just
I have
fast.
facet by the work level.
Well, yeah, that's it. Okay.
And in this one, I had facet by children. Again, I'll tidy up the code so it's not so nasty, but it was about 2 a.m. when I figured out a better way to do it. So I have the interpretation written out. Okay, so this is multinomial. It basically does, here with 3 categories, it basically does 2 different sets of logistic regression, so you get double the parameters. No assumption about those categories, those 3 categories having anything to do with each other. They're just different categories. Multinomial means many names. You can have just named categories. In this scenario, Mike pointed out working none, working part-time, working full-time is a spectrum. So there is order from less to more. So in that case, we could analyze this with the proportional odds logistic regression, which is also called ordered logistic regression or ordinal logistic regression. We got to have multiple names for things. Got to keep it exciting. Okay, this is how you fit it in R. You use the mass package, which I forget what it stands for, and the poly-R, P-O-L-R function. Other than that, it's the same. You say the variable that's the outcome, working, ord, because it's ordinal. And we're only going to bother with the husband's income and children. We're not even going to put region in there because we're just going to skip that. And which data set it is. You don't have to say family because this function only does polynomial ordered logistic regression, proportional odds logistic regression, POLR. Now, when we get the output, it's a little bit different. How many coefficients do we have? There's only 2. See, Mike, there's the value, the standard error, and the t-score, but there's only just for income and just for children. But what do you notice about where's the intercept? We don't have one intercept. What we get are several intercepts. So we only get one parameter estimate for each of our predictors, but we get multiple intercepts. The intercepts are often, I think Hoffman calls them cutoffs. If we have 3 ordered groups, how many cutoffs between the groups are there? We go from none to part-time, that's one cutoff, and part-time to full-time, that's the second cutoff. So sometimes these intercepts are called cutoffs. So we get 2, with 3 groups, we get 2 cutoffs, and then our regular parameter estimates. Now this is ordinal logistic regression. These are still on the logit scale. So the syntax is a little bit different. To get the cutoffs, to extract just these intercept cutoffs, we have to do the name of the model and then $sign zeta. The package people decided to call it. And that will pull out or extract just those cutoffs. And we can get confidence intervals for them. And we can, if we say coefficient, it'll give us the coefficients for the predictor variables, which we can then exponentiate. So let's interpret, these are the exponentiated coefficients. Let's look for income. Can we interpret the exponentiated coefficient for income? What number are we going to compare it to? Above or below 0 or above or below 1? 1. Is it above or below 1? Below. So for every $1,000 more the man makes, the chance that she works goes down about 5%. What about children present? If there are children present, the odds that she's gonna work goes down 86% to almost nothing. Okay. So we can interpret these exponentiated coefficients or get predicted probabilities, but the best thing to do is to make a plot, and it's coming, boom. Does this look the same as our other plot? It kind of does. Look at the children present if they're or absent. If there's no kids and husband's making a little bit of money, what's the highest thing going? The most likely thing is that she's working full time. And as husband makes more money, instead of working full time, she's going to stop working full time and start working not at all. And we see in the children present, what's the most likely thing no matter what? Not working at all. When does women work? Only if the husband is on the very lowest edge of the income. Okay. So this, I mean, we could flip back and forth. They look fairly similar. There are some slight differences, but it's telling much the same story. So which one's better? Multinomial or ordinal logistic? Both of them are options here. How do we know which one's best? We can compare the model fits. The easiest way, now these are not truly nested models. One has two sets of parameters, the other one has one set of parameters and multiple intercepts. They're not truly nested within each other, so we can't do the likelihood ratio test, but we can do our performance, compare performance. And that will print out our AICs, our BICs, our R-squareds, our RMSEAs, Bayes factor, whichever they have. Now, if you look at the multinomial, the Bayes factor is 1. Notice on the ordinal logistic, which value does it not have? Ordinal logistic can't give an RMSEA, but let's see. Let's look at the Bayes factor or AIC. The best model will have an AIC that's bigger or smaller? Smaller. So which model fits better according to AIC? Multinomial on the top. For BIC, which one does it say fits better? The top model, the multinomial. What about R squared? We want R squared to be smaller? No, we want R squared to be bigger. Which one has the better R squared? The multinomial. RMSEA we can't compare. The Bayes factor you want to be bigger. And the performance score we want to be bigger. So by the model fit, which of the two options fits our data better? The multinomial. And in this case, it's because even though working part-time falls in between none at all and full-time as far as number of hours a week, it was so like not even an option for most of the women that treating it as multinomial fits the data better than an ordered logistic regression. Okay. I flew past, the alarm went off for the break and I just kept going. Let's take a 5-minute break. And we'll come back for the last 20 minutes. Zoom recording. Okay. So we have like just over 15 minutes left is all. So I wanted to talk a little bit about probability versus likelihood, because this was something that there was discussion on the discussion board. And it is a very confusing topic. It's something that I almost feel like is water. If you try to hold water in your hands, you try to grab it and you think you have it and you open your hand and it's gone. The concept of likelihood versus probability tends to be one of those concepts, at least for me. And it's taken years to kind of feel like I'm more holding that concept in my brain without losing it. So probability, most people are okay. That's the frequentist point of view. We think of a parameter as a set value that we don't know. So what's the average life expectancy of all people in the United States? There is one true value, even if we don't know it. There is one true value. And we take a sample and we get the sample average to estimate that. Or if we want to know what proportion of people are going to vote for a certain candidate, there is one true proportion out there, but we'll take a sample to get an estimate of the proportion, or we have a probability, or given if the average height of men USU is 5'10", if we take a sample, what's the probability we'll get an average of 6 feet? We can get a probability if we assume that we know the population parameter, we can find the probability of a sample. Likelihood is the reverse. We assume we know the data and we make a statement about how likely a certain population parameter is. And that feels really uncomfortable because shouldn't the population parameter be known? But let's think about when the computer's fitting some of these models. Any of these models, most of these are fit with multiple maximum likelihood. It's time for the day to be over. So in maximum likelihood, where do we start from? We start from the data. And what is the thing we don't know? We don't know our betas and gammas, and we don't know our parameters. So we are estimating our parameters. How does the computer pick those numbers? It says, if this data is the truth, what's the most likely value that that parameter is? And if we think about fitting linear regression, ordinary least squared, we have a bunch of data points. We draw a line and we say, we count up the residuals and square them. That's a way of looking, capturing the likelihood. And so we might say, is the line here? And we see how likely that would be given our data. And we fit a different line and we do the calculation to find out how likely that's the truth. And we find the set of parameters that are most likely given the data is true. So it's the same equation. It's just whether you assume that you know the data and you're trying to find the parameters, or if you know the parameters and you're trying to figure out what the data should be or could be. So it's probability. So given the parameters, what's the probability you get a certain set of data? Or given the data, what's the most likely truth for the parameter estimates? That's my best explanation, which is not too jazzy and probably a little bit lacking. Anyone want to bring up anything about that? Is that helpful or still kind of water slipping out? We're all tired, huh? Candace, you look tired. Long days. Okay. We'll start. I was going to see if we didn't start. Okay. This is the last thing we're going to talk about today, obviously, because we're about out of time. So we've already seen today examples of extending logistic regression with 2-level outcomes into 3 or more level outcomes with either multinomial or ordered logistic proportional odds regression. We're going to kind of switch gears a little bit. This is the last kind of extension we're going to talk about it, and it's for when we don't have categories as our outcome, we have a count. The most common count is we're counting the number of occurrences or number of something over a given amount of time or over a given geographical region. It's not out of a total. I want to make sure that's clear. So we're not saying how many car accidents are there out of the 3 people in my family. So it could be 0, 1, 2, 3. We're saying how many car accidents were there at the roundabout down here on 2nd Street on last weekend between Friday and Saturday. So in a given time and or geographical region, how many occurrences? The lowest it can be is 0. It's got to be a whole number, 1, 2, 3, 4, but there's no hard maximum. Theoretically, it could keep going. Now, there is always a observed maximum, but there's not like, it's not out of 100 or out of 12. Okay, so this data set, oh, I got to go to the next one. This is the last one that's in here in the encyclopedia so far. Okay, so this data set has volunteering, right? This is our dependent variable, is volunteering. So the variable here, volunteer, a lot of people are zeros. That's the most frequent category, is not volunteering, but it's like how many times they volunteer. I think it's in a month. So there's quite a few ones, there's quite a few twos, there's less threes, even less floors, and it trickles up. The maximum observed number is 9. So if I plot it, it looks like this. Now, would you say this is a normal distribution? Hopefully all of you are shaking your head no. This is not a normal distribution. Yeah.
I don't get why, if you scroll up back to that table there was. I don't get why, if the volunteer hours is the like outcome.
Number of times you volunteered in a month, number of times. You don't get that it's what?
I guess I just don't get that, like why like an individual isn't in the first column. Like,
oh, this is a summary table. This is table F.
Oh.
The actual data set looks like this. The first person volunteered 0 times. They were a female, non-white with 12 years of education and $10,000 income.
Sorry, okay.
And person number 4 only volunteered 1 time. They were female, white, 12 years education, and we don't know their income. So yeah, the data set, it's a 0, 1, 2, 3, 4. But to explore it, I did a table F, which gives us the frequencies of each of those counts. Now, I kind of skipped over this data set, Joey, because if you look at this data set for volunteer, it looks like everyone's either 0 or 1. But that's not the case. There are mostly zeros, with 1 being the second common, and then it trails way off. And this data set is pretty big. There's 20, there's almost 3,000 people in this data set, so it's pretty big. Oh, see, the axis goes up pretty high. So this kind of stuff happens all the time. When the thing we're most interested in as a dependent variable is not continuous, it's not binary, it's not 3 levels, it's the account. And when you plot it, it's something crazy like this, where you have this J-shaped drop off. So the 2 keys here are that it's not normally distributed, it's skewed usually, and it's only whole numbers. Now, just because we ask number of times doesn't mean it's going to be plotted like this. If I ask number of times people had volunteered in their life, do you think it would look the same as this? What would the average be for number of times someone volunteered in their life? The average, what might it be? Anyone have any guesses? How many times have you guys volunteered in your life? Like, we'll just make it really vague. Anything volunteer. 20, 50, most people are going to be a little bit bigger number. When the average number is quite large and there's quite a bit of spread, sometimes we can treat it as if it's a continuous variable. Number of times can be treated as a continuous variable if when you plot it, you see something that looks kind of like a normal curve. But when we plot this, the average number is very, very small. It's most of the people are in the 0, 1, 2, 3 zone. And so the fact that there's no one in between 0 and 1 and nobody in between 1 and 2, because it's a count, makes it so you should not use regular linear regression. And if you do, the residuals will look horrid and any of your p-values will be probably wrong. But there will be no stat police to stop you. So this is the scenario where we want to use a type of regression that's made for dealing with counts. And the 2 that Hoffman covers that we're going to go over in GEEs and GLMMs are the Poisson and the negative binomial. Now there are 0 inflated versions of those that I have a little bit in here, but the Poisson and the negative binomial are the most commonly used. So here I have it broken out by sex. So this is, I love it. The default colors make men coral and females teal. But can you, looking at this plot, as terrible as it is there a relationship between male-female status and number of times someone volunteers? Chung-Soo, you're nodding your head. What is it? What's the relationship?
Females has more doing volunteer than male.
Males are coming out higher than men. Now that's as a count. Is that just because we have more women in our study? I don't know now. We need to take that into consideration. But yeah, the women bars are higher than the men. So we might want to see if women really do volunteer more, or maybe it's just that we have more of them. So Poisson regression. Poisson regression, we're going to go back and use the GLM function. So we have to tell it a family. Now check out this family. We're using the Poisson distribution, and we don't use the logit. Instead of the logit, we use just the log. Now this makes Poisson different. So we still are going to want to exponentiate our coefficients, but instead of them going from a logit to log odds to an odds ratio, they're going to go from log number to a rate. So it takes a while to get used to interpreting them. So here, the estimate for female, let's see. Here's the coefficients part. Estimate for female is 0.09. I don't know what that means because it's a log of the rate. But if we look over here at our Wald test, we see that being female, is that changing the number of times they volunteer? Not statistically significantly so, because the Wald test has no stars on it. Now, there is something on this output down here that comes out. Important to note. It says the dispersion parameter for Poisson taken to be 1. This is the part where the mean and the variance are assumed to be equal. That's a 1-to-1 ratio. That's why the dispersion is 1. When we look at, do we have it here? Did I do it? I didn't. I should have done that. If I took the number of time variable, number of times they volunteered in this month or whatever, if I did the average and I did the variance, I'm going to assume that those are essentially the same number. That may or may not be an assumption that's valid. Poisson assumes that that's valid. And how do you feel about making an assumption at this point in your statistical career? Blindly making an assumption? We probably ought to check it. So you can get estimated marginal estimates. So here I said on that model, do the estimated marginal means for female. Now, it's important to note that it will give this to you on the log scale. So it says male, it estimates males at -1.15. Does that mean they're going to volunteer -1.15 times? No, that makes no sense. You have to exponentiate to go back to the regular scale, and it's called the delta, gives us delta standard errors. So let's see. Yeah. Okay. So the TechReg helper function works here too. Now, I want you to know down here in the table. So here are the betas and the standard errors from the model, that -1.15 and +0.09. Those are the log scale. If we exponentiate, it puts it to a RR, a relative risk scale. And this is something I want you to focus on when you're reading Hoffman, is how do you interpret this risk ratio, and how is that different than an odds ratio or a proportion for that matter? So next Tuesday, we'll come back and we'll do a little bit more of the Poisson and the negative binomial. Negative binomial and Poisson are both for counts, and they have this assumption of dispersion being 1, the mean and the variance being the same. That's Poisson. Negative binomial relaxes a little bit and says the variance might be bigger than the mean. And so you fit an additional parameter called the dispersion parameter. So I will stop it there for today and let you guys go ahead and do the reading and video and for this material, the Hoffman chapters 4, 5, 6, and then you can start working on your logistic regression. I'm not going to give you an assignment on Poisson, negative binomial, and the other kinds of logistic regressions unless you want to do a homework 7 about it, you make up. Otherwise, we'll just focus on the concepts so that we can next week get into GEEs because they're cool. Okay, I'll hang out for a minute if anyone has any more questions.
Thank you.
And Candace, oh, she left. I didn't get to tell her. My plant's gone.
Thank you.
Hey, bye, Jill.
Can I ask us something about the project? Yes, I did some basic analysis. But
Yeah,
I
did you
haven't-
see my email?
Oh, I didn't get your email.
Yeah, I looked at it before class.
Oh,
And this looks really, really good.
oh, really?
Awesome. Yes. So we want to start with number 1. So this plot, I'm not sure. Just not sure about this plot because it's doing a scatter plot and it's connecting the two people. I think we might want to have time be on the x-axis. I don't know.
Oh, that would be a research question too. Research question 1 is just doing the cross-sectional analysis.
Yeah, but this one I kept looking at it being like, it's connecting. So this is the first person's pre and post test, and
Yep.
this is their partner's pre and post test.
Yes,
So
you're
I just
right.
didn't know how useful this plot was. Like if it's this way versus this way, that doesn't really give me any different information. The length of the line is how far apart those two are, but I didn't know how helpful
yes.
that was.
Yeah, I just wondering the distribution of the pretest, and I just want to check the relationship between the pretest and post-test. So
Yeah,
that's
so I
why
would probably take the lines off and just do the point for this one.
I see.
Just as
So
a scatter plot. And I think you did, that's what you did here.
Yep.
So this is the scatter plot, but with the geom count for the overplotting and the density and the smoother. So this one was definitely spoke volumes. This one told me about pre-test and post-test definitely associated.
Yes.
And I get that you were trying to somehow connect the partners or the people triads together, but I don't know. It's a good attempt. Okay. So you did null model and ICC, that looked good. That is quite a bit of variance. And then gender and pretest, and yes, they show up as pretest is significant, gender was not. And then you add in the average.
Yes, that is a sharedness, similarity game behavior. And I just averaged 6 time points.
Yep, so that's significant. And then the last one, the gender being the same.
Yes, as your recommendation, I made a categorical variable. So if the gender has the same, if members consist of the same gender, I made a variable like a
Okay, so this is saying if they're the same versus different. Okay.
Yes,
so what's this within difference?
In our area, in team collaborative learning, the differences in prior knowledge is really.
So it's a pre-test difference.
Yes. So but it is very hard to make a variable. So in the literature, if I did a literature, I searched some literature and some articles using a Gini coefficient. So to measure the
similarity.
Differences.
Or difference, which is the opposite of similarity.
Yeah, you're right. So that's why I recalculate and make this variable and enter the model.
So I think that this was perfect. The only thing that I could say here is to fit one more model and to leave in the pretest, and I would leave those two in and then I would take out the now I would start paring it down, taking out the non-significant terms.
So you
So-
mean is
So this
the
one has,
to
I'd
make
take
a
out
more
gender,
Mhm.
and I would take out within difference, because this one is so close to being significant.
Yes.
I think if you take out those other two that were so non-significant about their own gender, and if the group was same gender, that I think it has the potential to clean this up.
I see.
It's not a guarantee, but we do know that the parameter estimates and significance in a model depend on what else is in the model. And if you have these non-significant variables in the model, they can reduce the power away from other variables. So that's the only thing I would suggest on this one.
I see. So I give it a shot of removing those two variables and check the model.
And I wouldn't be surprised if this team gender being the same variable might have the p-value might become significant with the increase in power by removing two non-significant variables. Not guaranteed, but something to try.
I have a quick question. In this table, I was wondering why the degree of freedom, like a number of a group and team. So null model, and in level 1, there is a 74.
Oh, the sample size?
Yes.
There must be at least, there's got to be 5 teams that are missing this within difference score.
Oh, so how can I handle this issue? Because I tried to
Do the ANOVA, the likelihood ratio test?
Yes, that is something. I faced something error in doing ANOVA analysis.
Yes, that happens all the time. Let me see. Because when you add variables to the model, if the variable is missing for some people, then they're not the same data set. So let's see, I'm trying to remember. Okay, right here. So that's what happened in this model. My first model had just 1 predictor, and my second model had 4 predictors. So when I fit the model with more predictors, since people are missing on those, it shrinks the data set. So what I had to do is I had to refit both models to complete cases. So I took my data set and filtered it down to just the people that were complete on all 4 of the variables. And I saved it as a new named data set. And then I had to redo both of my models with that reduced data set, so that when I would have, now this is single level, but it's the same principle, so that they were fit to the same data, so that I could then do the likelihood ratio test.
Well, I have a question. When doing the MLM, we have data including some missing data. When we do ANOVA, we just doing the complete data. So is it rigid? Because the data is a
Well, in that one, it was refit because those models were fit with REML. So the refit depends on if the models were fit with REML or ML.
No. What I want to ask is the data set in MLM has missing data.